Alright, let's equationize this stuff. So, last time we talked about the three big variables we talked about waves: amplitude, frequency, and wavelength. And amplitude is kind of a big one. We don't really use it a whole lot in equations, mainly because it's so hard to quantify for all the different types of waves, but like all waves will definitely absolutely have an easily measurable frequency and wavelength. So those are the two big ones. We're going to add in a fourth one that'll be kind of a new big three. So amplitude is going to get kind of shoved out of the way, and this new one's going to come into prominence, which it's still not. It's really just wavelength period. But anyway, you should have a blank version of this handy dandy little chart. And if you don't, you should copy it down. Like if you don't have a printer or whatever, that's totally fine. But you should definitely take a minute or two to copy this down. So I will wait while you do that. Loving these low-key beats. I don't actually have to wait because you can just pause this video, right? So I don't need to like do this whole dance break for you. But whatever. Okay, cool. Anyway, so we're going to assume that you have this chart in front of you now. And we're going to organize this all out, right? So we would have done this with, vocab sheets and things like that, but this is, there's only three of these that you're going to regularly refer back to. So we'll take a look at it, right? So wavelength, we already said that was the Greek letter lambda, and we talked about how to do that, right? How to write that. Hey, where'd my color go? I want my purple color back. Yay. Right, so we just kind of like bam, 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 like that. Like if you want to get fancy, you can kind of do that. It's really, ooh. And I did just buy like a whole touchpad thing that I should be practicing with. But anyway, bam. All of those work as lambdas, which is spelled L-A-M-B-D-A. Lambda. Except the B is silent, like Mary had a little lambda. And that's the Greek letter lambda. Be like, well, wait, I saw Revenge of the Nerds, and they were lambda, 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 and those are you probably have not seen Revenge of the Nerds because it was a movie from the 80s. Don't watch it. It's very problematic. But, yeah. So, which also kind of looks like delta, right? It's all weird. Delta is actually more of like, kind of like an angled one. It's more like, more like that, technically, where lambda is more of a traditional triangle like that. But this isn't a Greek class. This is a physics class, so we're going to just not worry about that right now. So lambda, wavelength, it measures how far the energy travels with each complete oscillation. All right, we want to think of like waves as steps, right? The you are the energy, and each step you take is a part of your wave, right? And wavelength is how big your steps are, how big your stride is. And we measure that in terms of length, how far you travel with each step that you take. Frequency, lowercase f, is just how quickly those vibrations or oscillations occur. So that's how quickly you're taking your steps, regardless of how long they are. We're talking about how many steps per minute are you taking. Right? Those of you with your Fitbits are like very clear about how many steps per day you're taking. So, which again is a frequency, right? It's kind of like how frequently you're taking steps. Now, measuring this, this is kind of we didn't talk about the units in the last video. So, units of frequency. It's really just like how many oscillations are happening per second, like how quickly the oscillations happen. So how many times you're going up and down in a set period of time, typically seconds. So it's really kind of like vibrations or oscillations, but that's kind of a counting number. So it's really just the units are technically inverse seconds, seconds to the -1. So you'll often see, oops, let's go back. Oh, sweet. Oh no, go back. Cool. So you'll often see frequency written as seconds to the -1. Just means inverse seconds, right? And we know how fractions work. If we see this, right, if this is like seconds over 1, we know what to do with this seconds, right? We put it in the denominator, right? 1 over seconds, right? Because these are all vibrations per second, oscillations per second, right? Anything per second. So seconds per -1, seconds to the -1 rather, the inverse seconds. And so hertz is really just equal to, I'm going to use the pen this time, is equal to seconds to the -1. Just inverse seconds, right? It's oscillations, vibrations, because because frequency is it's like a universal unit. It's not just used for waves. It's used for any kind of like frequency that things happen. Like if you take a look at this little AC adapter here, I'm going to try to hold this up to the screen and show you. I don't know if you can read that or not, but there's a little section there that says input 100 volts to 240 volts AC, right? Because we know AC comes out of the wall at 50/60 hertz. What that means is the alternating current is going back and forth, turning on and off 60 times every second. So, yeah, hertz is used as frequency for like anything, not just waves. So that's why they refer to it in general as inverse seconds. But we know with waves, we're going to always be talking about it in terms of full oscillations per second. And so so now we can go into here. And this is something we already kind of talked about, right? We talked about this kind of inverse relationship between wavelength and frequency when we keep the speed constant, right? So these two waves here we talked about are traveling along at the same speed. The energy is traveling across the screen at the same time, right? The red and blue energies get there at the same time. However, we can see there's an inverse relationship here, right? So the wavelength with the longer waves, the one that's taking more steps, doesn't have to take as frequent of steps. They don't have to take as many steps to get there because they're traveling further with each step. Whereas this one has to take a lot more steps per second in order to keep up with the blue wave. So these two things are kind of inversely proportional when you keep the energy speed constant. And now, if we kind of like try to equationize this, right, we know that wavelength is distance per wave, and frequency is waves per second. But so we go, well, like, pause and take a breath there. What do you mean wavelength is distance per wave, Mr. T? You told me it's the length that each wave travels. Well, yeah, it's per oscillation, right? So, like, it's how far it travels for one oscillation. Distance per one wave. Whereas frequency is how many waves every second. And we know that the units of speed are usually length units divided by time units, right? V equals d over t, distance divided by time, here. So what can we do with these two variables here to get an equation for wave speed? So we got distance per wave, waves per second. What can we do to frequency and wavelength? Like, we can add, multiply, divide, subtract. What do we got to do to these two variables so that the units work out to speed units, meters per second? Yeah, we multiply them, right? Because if we do that, we get meters per wave and waves per second. Well, the waves in the denominator here and the waves in the numerator here, they cancel out. So we're left with meters in the numerator, seconds in the denominator. Meters per second. There we go. That's our, that's speed, right? V. So the speed of the energy of the wave is just the lambda times the F. V equals lambda F. Cool. And that's really the only main equation. The other one's kind of a definition of another term, just in equation form. But that's the really only main equation we got to work with here. V equals lambda F. Sometimes we'll use V equals distance over time, but that's an old equation. But that is an acceptable equation to use in some of our practice problems that we'll see later. But this is really it for waves. V equals lambda F. It's the only one, so it's not that hard. It's like the easiest math to do all year. We start off with like hard math, and it gets easier and easier and easier. As the concepts get harder and harder and harder, there's going to be way more vocab and stuff. So we will erase all ink. We'll get to that next term, which is period here. So period, which is an italicized capital T, not a regular T, italicized, angled, is how much time it takes for one complete oscillation. So frequency and period are really trying to describe the same event, just in inverse ways. Right? So frequency, we're talking about how quickly the wave goes up and down. You can talk about that and how many times it goes up and down in a second, or you could talk about it in how long it takes to make one oscillation. Right? Like if you've got a small period, right? If you've got a small amount of time for one oscillation, well, then you're doing them very quickly. Right? Like one wave that takes a whole second is oscillating slower than a wave that only takes half a second. So they're inverse. They're not just opposite. They're legit mathematical inverses. So to calculate them, right, period is seconds per wave. how long it takes for one wave. Frequency is waves per second. That is like legit mathematical definition of inverse. So to calculate the period of a wave, 1 over frequency. To calculate the frequency of a wave, 1 over period. And that's how we'll trip you up in some of these problems, because that's as hard as we can make it. Is we'll give you the lambda, and then we'll ask you, and we'll give you the period, and ask you for the energy of the wave. And you just got to remember to flip the period so you can get the frequency. And that's it. Sometimes we'll make it a little bit tricky to kind of see where the wavelength is, and you might have to measure it out and divide and things like that. But that's it. Those are the equations. V equals lambda F, italicized T equals 1 over F. That's it. But I want to talk a little bit more about this inverse relationship between frequency and wavelength. Because one of the most important things about electromagnetic waves, like we talked a lot about them. I think in one of the Edpuzzle that I didn't record myself, that they might have touched on this. I'll have to double check. But something really important about all electromagnetic waves, right? We said they're all the same stuff, right? Like radio, micro, infrared, ultraviolet, X-ray, gamma rays, they're all the same stuff. It's all just oscillating electric and magnetic fields. The only difference is how quickly they oscillate. But something really important about them is they all travel at the same speed. Radio waves, gamma waves, they travel at the same speed. Ultraviolet, infrared, travel at the same speed when they're in the same medium. Right? Like in the air, all waves travel at the same speed. All the colors of the rainbow, all the colors in the rainbow, they all travel at the same speed. Red light travels just as fast as purple light. It's like, but they oscillate differently. Yeah, but the speed of the oscillation has nothing to do with how fast the energy goes. Right? That can be accounted for by wavelength, which here it is. So it's a very important property. All electromagnetic waves travel the same speed in the same material. And even more importantly than that, the speed that they travel in a vacuum, when there's absolutely nothing in their way, is the speed limit of the universe. Fastest we can go. Absolute fastest. Can't go faster than that. 3 times 10 to the 8th meters per second. 300,000 something. I forget. I can't do that math right now quickly in my head. But 3 times 10 to the 8th meters per second. 3 with 8 zeros meters per second. That's the fastest thing. That's the fastest thing. Faster than anything. Let's Google how fast people have gone. Let's take a look at it. We'll take a break right here. Discard the annotations. We don't need those. All right, let's pull up the internet here. And we will say, what's the fastest we go? What's the fastest a human has ever traveled? Google. See. So the crew of NASA's Apollo 10 mission reached a top speed of 39,000 kilometers per hour. Let's do a little conversion of that, huh? So let's put this in meters per second. In meters per second, please. That's only 11,000 meters per second. That's only 1 times 10 to the 1, 2, 3, 4. That's 1 times 10 to the 4th meters per second. That's the fastest we've ever gone. 1 times 10 to the 4th. Light, and rather all electromagnetic waves, 3 times 10 to the 8th. You'd have to multiply that by 3 times 10 to the 4th, by 30,000. Multiply that by 30,000. And that's how light travels 30,000 times faster than we have ever traveled. That's insanely fast. That is insanely fast. And if you have any other questions about how fast things have happened, Google it. As you can see, it is highly Googleable. But let's get back into it. So let's visualize this, right? They're all traveling at the same speed. So let's take a look at a beam of white light. What do you mean, Misty? That's a rainbow. Yeah, we talked about this last time, right? White light is a combination of all the light. All the different colors. All the different wavelengths. So they all are traveling here at the same speed. Right, did you see it? Right, let's see it again. So they all travel across the screen at the same speed. So the white light, all those different wavelengths are traveling at the same speed. But let's separate them out. Right, so they all travel at the same speed. But as you can see, if you compare the top and the bottom, the purple has to oscillate much quicker to keep up with the red. Now again, these aren't to exact scale, but it's a good enough approximation for us to kind of see this here. because I think they'd actually be even worse. Like I don't think I did any kind of math proportions for this, in terms of like how quickly they're going across the screen versus how their wavelengths are here, like proportionally. But that's what's happening. So as you can see, it's tough to see when you combine them all together. So let's just like take a look at the biggest and the smallest, red and violet, and a good intermediary one. The energy's going across the screen at the same time, but the purple one has to go up and down much quicker to keep up with the red light. Because again, they're inversely proportional when the speed is the same. When the speed is the same, the wavelength and frequency are inversely proportional. Bigger steps, less oscillations to go at the same speed. So at this point, what questions or connections do you have? Yes, we're going to do some practice problems. And yes, I'm going to post some walkthrough solutions for those. So be on the lookout for that. So yeah, what questions do you have? I like that. Post them to the board, please. And if I don't see them, then I will catch you on the flip side, which is a weird thing to say. Sorry.